start a recording. Yeah. Well, as the concept of matrices, that will be used as a compact representation of coordinates systems, both 2x2 and 3x3 matrices, and in very many respects, matrices can be added, subtracted, and multiplied as normal numbers. It's just a arrangement, 3x3 arrangement that will be the most common matrix. They're used for rotation matrices. Let me take an example. Now let's see, whiteboard. So if you should, if you have a vector, we call it x, y, z, and we should rotate it, for example, so it should become y, x, z. And the values here could be denoted by the actual coordinates along the x, y, z, or a, b, c in the real space. So a convenient way to express this is by a rotation matrix, where we take the first row scalar with that component, that column vector, and we should have this is the result. Then we take we shouldn't the first element should be the scalar product of the first row and the column vector here. So it's 0 times x plus 1 times y plus 0 times z. This is actually y. And then we have 1, 0, 0 and 0, 0, 1. And so this could be called a rotation matrix. I try to make it bold face or something, double sign like that, times a vector x is a new vector x.
I'm sorry, Professor, can I ask a question?
Yes, of course. That's very good. You should interrupt. Yes, please. Let me hear.
I mean, it's probably ultra basic. How did you get these numbers 0, 1, 0? I mean, I know the rule how you multiply matrices, but where did you get the numbers 0, 1, 0, 0, and so on?
Yeah. Good question. If you take these two vectors and multiply them as 0 times x plus 1 times y plus 0 times z, then you would get
I get. You already knew the result. Okay, yeah. So that's why you wrote. Okay.
And then we take the second one times the same column vector, and we get the second element.
Yes, okay. Yeah. Okay, it's very very basic. Okay, cool. Thank you.
Yeah, but it's very basic. There's nothing wrong with that. I mean, it's no more complicated than this ever in this course, I would say. You could, as soon as you get into non-orthogonal coordinate system, then it will be a mess. Hexagonal and trigonal coordinate systems is usually difficult, but as soon it takes an hour or 2 or 15 years or something like that to sit down with the paper, and suddenly you realize that it's quite convenient. Well, I don't think we should actually. Yeah, we should perhaps do this manually, but also we should use a computer program to simplify calculations. Where is my view graph? Here. And one can use these rotation matrices in order to define symmetry operations in something called sites nomenclature, sites operator nomenclature. So multiply coordinate vector x by a rotation matrix, add also translation vector, and then you get a new coordinate vector. This will become apparent when we we have something to calculate on and something to deal with. If it's mysterious now, it's not so problematic. Matrices, and matrix A, for example, usually has an inverse. With the property that the inverse times the original matrix A is equal to a unit matrix. E is just a matrix with zeros except on the so-called main diagonal, it's units. This could be of interest. I mean, it's quite convenient to formulate and solve equation systems, because then you could, for example, use some software, MATLAB or Octave, essentially equal. If you have MATLAB installed on your computer, then it's no reason not to use that one. But if you don't, and if you want a simpler system than MATLAB without any license requirements, then I recommend Octave. We could vad händer nu då? Så. We could see if we can start this Octave system. Personally, I'm starting it from the command line, but that is not necessary. Do you see my Octave working directory, something here?
Yes.
Yeah.
Yes.
So I have it set up as a command window and hoopsan, no. And a file browser here. Let's see if the default setup is something like this. Then I usually close these two, make this one a little bit bigger. No, let's see. We can define the vector within brackets, and then say that we have 1, 0, 0. Either use blanks or commas. I think one can use commas if you like. Yes, that will be a vector A. We can define a vector B as 0, 1, 0. 2 unit vectors along in the X and Y direction. So what happens if we can do calculations with these two? That is not defined. No, then it says operator 1 is 1 by 3 and operator 2 is 1 by 3, and this with 2 row vectors it is actually not a defined operation. But if we change the row vector to column vector with this little single apostrophe, so then we see if we can. Yeah, that was 0. Why is it 0? Well, it's because the scalar product, the projection of A on the column vector B is because they are perpendicular to each other, and they are cosine of it is the angle in between is 0, so that is the so-called dot product. One can also make dot A, comma B, that is the same? Is there a cross also? Yeah, that is the dot product of A and B and the cross product of A and B. The cross product of A and B, A was the X direction vector, B was the B direction vector, and the cross product is the C direction vector. All three of them are perpendicular to each other. Let's forget this. One can also define a matrix. We call a matrix A. Within brackets, say that its first row is 101, and I don't know what I'm writing, so I'm just typing. No, we shouldn't have two similar. Here are three different first row, second row, and third row. They are marked as different rows by being divided by semicolons. So then we get, this is in a way a rotation matrix, a strange rotation matrix. We can see, can we invert it? Some matrices are not possible to invert. If there are two, if we would say that we define a matrix like this one with two rows similar, and the third row different. I mean, it's a valid matrix, but does it have an inverse? We'll see what Octave. There are some problems actually obtaining. Octave doesn't crash easily, but this is an undefined matrix, and we can calculate the determinant of B. Then it will be 0, and this is equal to, you can't invert the real number 0, because that will be, well, you can say that one upon a real number, when the real number approaches 0, then the inverse approaches infinity. But infinity is not a defined value in very many senses, in the sense that, well, for example, 7 is a number 7. You can very clearly define what is, how many objects in a set of 7 objects there are. But an infinite set is more difficult. There are an infinite number of integer numbers, for example. But there are also an infinite number of integers bigger than 0. So that's strange. Yeah, I will. There are a lot of use this Octave or use some similar system for doing calculations. Of course, one can also do calculations by hand or by other type of specialized systems. Vectors and matrices is the ideal objects to handle with Octave and MATLAB. MATLAB is an acronym for Matrix Laboratory. Complex numbers is we will also encounter. They can be described as vectors where the components are real numbers, and one of the components are multiplied by this imaginary unit I. So in Octave knows I. So if you define something and call it I in Octave, then Octave will forget the original definition. So that's a risk in a way, but it's not a big risk. Similar, if we see a complex number as a vector, then we also have a Cartesian and polar form of that vector, just like normal 2D vectors. And complex numbers can be added, subtracted, multiplied, and also divided, even though division and multiplication is slightly more complicated than with real numbers. It's more or less the same thing. MATLAB and Octave, they have everything defined in the complex number system, so you don't need to care about the actual problems. If they show up something multiplied by I, then you're in the complex part of the number system. Then you left the real number line. That is not a problem, but it's just a little bit uncommon. Sorry. With the complex numbers, it's sometimes very easy to make very compact representations of say e to the I alpha. There is one of the Euler identities. Euler was a very productive man. He wrote 70 books or something like that in the 17th or 18th century. But this is a convenient relation that we will use very much when speaking about structure factors. And finally, yeah, the final slide here deals with something called group theory. A group, a mathematical group, is some kind of structure and relations between objects. And if I mean the idea that why should you study group theory a little bit at least? You can make a PhD in group theory, maybe not, but in algebra at least, and possibly also in pure group theory in the math department. But don't overdo it. Do it a little bit, and maybe the part that we encounter here in this course is enough for crystallography. In the international tables, there are a lot more described about algebraic structures and group structures. The concept of a group, there are some axioms. There need to be a set of objects. Anything in principle will do, except the empty set. The empty set is not possible to use to define a group. But if you have several empty sets, then perhaps you can use them. But how to distinguish one empty set from another empty set, that is, no. Let's not complicate it. We have a set of objects, coordinates, numbers, operations, matrices, anything. And then we have an operation associated that we should let these operate on these elements with. There should be one element that has the property of being an identity. I will take some examples soon. Only one element, similar to if you have the set of integers, they are actually an infinite group under addition, with the operation equal to addition, and the unit element of the in the set of integers is 0. Because if you take an integer plus 0 or 0 plus an integer, you will get the same element back. Let's make an example. We take the set of integers 1, 2, 3, 0, -1, -2, an infinite set. That is probably a problem if you want to count them, but let's just say that they are infinite number of elements. There are a lot of elements, and to say the no, we don't do it like that. Say to the element A, there should be a unit element, so that A, this is the operation, but let's say that the operation should be plus. Here we have the set, and here is the operation. So A plus the unit should be A, or unit plus any element A. This should be valid for all elements in the set. If A, no, E is 0, then it's okay. And there is only one element that is a unit element. It should be closed. So if you the set should be closed, or the set describing there should be no way to add two integers, say A plus B, then you get another integer, possibly the same if one of them is a unit element. This is also an integer, so it's inside the set. This is okay. This was the inverse. What was it now? Closed inverse exists. No, this was not at all the inverse. It was the unit element. The inverse should exist also. To any element, there should be another element so that we have the unit element. Is this valid? If you take 2, for example, is there any element that you can add to 2 to get 0? Well, yes, -2. And to every possible A, there is an B that, or one could say to every possible A, if we denote by e to the minus a to the -1 here, the exponent -1, the inverse, then this is E. So then we can say if all of these is fulfilled, then we have a group. But for example, suppose we have the natural numbers. Those.
Excuse me, Professor. I have.
Yes.
I have also a very simple question. What does it? What did you mean by saying that the system is closed with this like A plus B equals C? I understand that for each. Okay, I will let you to.
Yeah. For each, any element operated together with another element, in this case plus, you will get a third element, and you will stay within the group.
Okay, and the group is defined, but set is infinite, right?
Yes, yes.
Okay. I get it. I get it.
But the natural numbers, possibly with the inclusion of 0, if we add 0, then we will have a unit element. This is okay. And the sum of two natural numbers, that is okay. But the inverse to any number is not okay. So the natural numbers under addition is not a group. Then we can say that the set of natural numbers have, in a way, a different property than the set of integer numbers. This is perhaps very abstract. We'll see. Let me go back to what was the clear. Så nu ska vi se. Yeah, let's go to something called limited set. And then we can construct a group table, any possible combination. Say that you have a set of 2 elements only, and with some operation. If it's numbers, then we can have an operation of plus or minus or multiplied or any operation. Then in order to check if this is a group, let us, we assume that it is a group. So we set up a quadratic arrangement with the elements and in 2 versions. And then we argue like this: is E times E unit element operating on a unit element that is by definition a unit element, and unit element on A must be same as A, and A and unit element must be same as A. So a group table now, what is A times A? We don't know, but one element should occur only once. Only once in every row or column. So if we say that this should be A, then then this is not a group structure, because A is present 2 times here in this column and in this row. So then we need to set this to E. Then we have the property that E times A, E and A is present once and only once. Each of one is represented, and each one is represented once and only once in each row and each column. Then we have something called the group table. Now we constructed the group table, and perhaps what do we have an example of such a group? Yes, we have. For example, we have several examples of a group. We could say that it's the group of equivalent positions x, y, z, and minus x minus y minus z. Here is the bar meaning minus. This is 2 objects related by a simple symmetry operation, but we can call them A and minus A. And suppose if we say that this object is, or that we say that this object is represented by a rotational, it's difficult to have a it's difficult to have anything that one can calculate with. Let's say that this is the rotational representation of an object XYZ, and then this is exactly same for the minus x, minus 1, minus z. And then we can just, if we multiply them together, then we will get one of them as, take one of the objects and select another object, possibly the same. If we select the second object, we will get this object back, which is, if we call this E, then this may be called A then, or A, and we'll rename them. Oh, this was a bit confusing, maybe. Let's take another example. A triangle. Are there any symmetries present in the triangle? Well, if we rotate one third turn around, say, I'll make a triangle here, so then we will get that one. No, A and B and C, and then another one. We will have A here, C up here, and B here. And then another third will return back to that one. So these three orientations, we can say symmetry-related orientation of a triangle, they constitute the objects of a group, because you can't get outside this group by performing the rotation. The operation is the 1/3 operation rotation. You can perhaps say that, what about if we rotate 1/3 to the other direction? Yeah, but that's equal to 2 times 1/3 in that direction. So that's nothing strange. Is this a group? It's closed, definitely. You can't get out, you can't obtain any other configuration of a triangle by rotating it a third turn, at least in 2D space. Is there a unit? Is it a possibility for any object to be transformed to the same object? Yes, it's just doing a full turn rotation. Yes. Is there an inverse? If we take, for example, this object constructed by the operation by rotating the initial object 1/3, yes. Can you get back to this one? Yeah, why not? Either you say that you rotate back, or you rotate 2 times. So then we will have the unit element. So this is a mathematical group. Very convenient. Well, maybe not so convenient for a simple free cornered triangle. But if it's a molecule with a lot of symmetry elements present, in the molecule, then it could be convenient. I assure you, it is convenient. This triangle could be visualized by a group table also. And the main row and column here is the same, because multiplication by unit doesn't change anything. But multiplication by A and A can't be A, but it can be E or B. Is it, what should we choose? We can choose E or we can choose B. Any voting? B?
E.
E? E, okay. Then this one, AE, it must be B because, shit. Then we take the other possibility here. If this is B, still we have the reason A, B, then this could be E. Yeah, that fits. So far, A, B, then this must be E. Because it's only E left, B, E, then this could be A. Yeah. This is the group table 3 by 3 for a third order group. And since we haven't actually decided any meaning of the elements, this is the only third order group, one say. The order of a group is the number of elements. Maybe a bit surprising, but with the triangle and the rotations in 2D plane of a triangle, you have actually covered any possible third order group. They are not very common. Only one third order group. If you have order equals 2, there is also only one of these abstract groups. This is a mathematical abstract presentation of a group structure of a set with 3 elements, and we did not necessarily define what kind of operation that should be present, but if it should be a group, there should exist a group table like this. For order 4, there are actually 2 different groups. Only 2, but then it gets worse. For say order 8, there are I don't know how many different. There are several different. And when the number of elements increase, then the sort of group structure is a lot more difficult to prepare. For order 5, by the way, this is only one different. 5 is by accident a prime number. Not accident, but it could have some relation to number of different group structures, if the order is a prime number or not. But well, 4 is not a prime number. 5, 7, 5 is not a very common order in crystallography. Actually, it is not occurring in 3D crystallography. There are no 5 order groups in 3D space. that are of interest. Of course, you can have a flower, for example, that has a 5-fold rotation axis approximately. If you rotate 1/5 turn, you will get the same indistinguishable picture of a flower back. So then you have 5th order symmetry in a flower, but that is local symmetry. You can't have a 5 order polyeder or something like that and try to fill 2D space or some 5th order 3D polyhedra and try to fill 3rd order space, not regular polyhedras at least. And if they're not regular, they're not 5th order. Sorry. So group table. There are some practicals listed in the lecture notes in the first chapter. There are also subgroups. For example, in a 4th order group, there is a possibility to have a similar structure in several. You can divide 4 by 2. This is something called Lagrange theorem. Still, also one of them. Lagrange was extremely productive. Not as Euler maybe, but still one of the. Now let's see, where are the I had a group structure. Do you see my group table here?
No.
No, sorry.
Here?
Yeah.
This is a 6th order group, one of them. A group table for a 6th order group with an element E and 5 different elements. And then we have it on the main, we have them on the main row here in the main column. And then I asked one of the possible fillings of this 6th order group table is like it's shown here. So E, A1, A2, A2, E, A1, this is okay. Or if you color it, you will see that you have a structure here. So this 6th order group is actually sort of, if you look at it, it's repetitions of a 3rd order group with, in a way, different symbols. But if you say that E in the red 3rd order group here means is depicted by A3 here, then you can see that A3, A3, A3 occurs at the same positions as E, 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 because 3 order, there is only one group. But then you say that this is a direct product of a 3 by 3 group with a 2 by 2 group. If you look at the red objects as one object, the object is a free 3rd order group. Why not? Very abstract, but what is a 3rd order group in physical reality? That is difficult, but in abstract reality, in mathematics, it's they don't care about this. So the red thing and the red thing can be interpreted as one object, and the blue thing as another object. So then the red, blue, blue, red is a second order group. Now, the idea is that a sixth order group can be possibly some of the possible sixth order, at least this one, can be factored in smaller groups, 3 by 3, then, and also 3 by 3 multiplied by a 2 by 2 group will perhaps make a 6 by 6 group table. But there are other 6 by 6 sixth order group that is not possible to factorize, but this very group is possible, and this is quite common actually in crystallography. So we will encounter very many cases where we have a set of positions, symmetry related positions, for example, but under some special conditions, special values of coordinates and such things, they could be factored down into simpler representations. 2 times 3 is 6, and 6 is divisible by 2 or 3, also by 1, but I mean, dividing by 1 is hardly necessary. A sixth order is also possible to divide by 6 in order to get a full number, integer number. So then you have the group with only one object. This is actually a group also. And this is a simple way to remember why is it only one group for fifth order. Well, there is no way to factorize a fifth. Could perhaps be other fifth order. I shouldn't say that. There is no way to factorize a fifth order group because 5 is a prime number. 7, 11, 13, etc. None of them occurs in crystallography. But 2, 3, 4, 6, 8, 12, such things, that they are common orders of group in crystallography. Now let's see. Time runs. I think we should make it yeah, there are some for this calculation exercise that occurs on Wednesday. We have some selected exercises from chapter 1 in lecture notes and chapter 2 and chapter 4. And there will be answers also available to these. I know Erik Rape has made excellent documents with answers. And you will have access to this recording also.
Professor, can we please get these slides in PDF as well?
Yeah, they are on both the Dropbox and the
Okay. Oh,
box area.
Okay, thank you.
I hope. yeah, but they are. In general, please don't hesitate. I forget some things, and my colleagues are not perfect humans, so also they forget things. So please let us know. But this one is uploaded. We should upload more. I think we should upload approximately as the course progress, but because there's no reason to upload old materials because we change maybe some parts. I stop the recording now.